The night sky stretches endlessly above us, a canvas of shimmering lights that has captivated humanity for millennia. Each dot of light is a star, a beacon of energy born from the very fabric of the universe. But have you ever stopped to wonder how these celestial wonders come into existence? What invisible forces orchestrate their birth, shaping them into the luminous giants we gaze upon? Today, we're diving into one of the most profound mysteries of the cosmos, the birth of stars, and not just any explanation. This is about the 24 celestial blueprints that guide star formation, a groundbreaking framework that reveals the hidden patterns behind the universe's most spectacular events. These blueprints aren't just for astronomers, they are for anyone who's ever looked up at the stars and wondered how such beauty could exist. From the swirling clouds of cosmic dust to the explosive forces that ignite a star's first light, we'll explore how these blueprints map out the universe's grandest creations. So, what exactly shapes the birth of a star? How do these blueprints guide the cosmic dance of creation? And why does understanding them matter to us here on Earth? Over the course of this video, we'll unravel these questions, piece by piece, as we journey through the awe-inspiring process of star formation. Get ready to see the night sky in a whole new light. Deep within the vast expanse of space, hidden among the darkness, lie the cosmic nurseries where stars are born. Picture this: colossal clouds of gas and dust, stretching light years across, swirling in a delicate dance of creation. These are the stellar nurseries, the universe's most fertile grounds for star formation. But what makes these regions so special? Why do stars emerge here and not elsewhere? The answer lies in the first of the 24 celestial blueprints, which reveals the precise conditions needed for a star to ignite. At the heart of every stellar nursery is a delicate balance. The temperature must be just right, cold enough to allow gas and dust to clump together, yet not so cold that everything freezes into stillness. The density of these clouds plays a crucial role too. As gravity begins to pull these particles closer, the material becomes denser, creating pockets where the magic of star formation can begin. But gravity doesn't act alone. It's the interplay of forces, gravity pulling inward, while pressure and turbulence push outward, that sets the stage for a star's birth. Astrophysicists describe these nurseries as cosmic cradles, where the raw ingredients of the universe come together to create something extraordinary. Imagine a potter's wheel, spinning slowly as hands shape clay into something beautiful. In much the same way, gravity sculpts these clouds, compressing them until the conditions are just right for a star to form. It's a process that can take millions of years, a testament to the patience and precision of the cosmos. But what happens when gravity takes the lead? How does this invisible force transform a swirling cloud of gas and dust into a blazing star? That's where the story takes its next turn, as we explore the role of gravity in shaping not just the birth of stars, but the very structure of the universe itself. Gravity, the invisible architect of the cosmos, is the force that breathes life into the cold, dark clouds of space. Imagine it as a cosmic sculptor, patiently shaping the raw materials of the universe into something extraordinary. Without gravity, those vast clouds of gas and dust would remain formless, drifting aimlessly in the void. But when gravity takes hold, everything changes. It pulls these particles together, drawing them closer and closer until they form dense, compact cores. These cores are the seeds of future stars, the first critical step in the journey from chaos to creation. Renowned astrophysicist Carl Sagan once described gravity as the great unifier, a force that binds not just stars and planets but entire galaxies. In the context of star formation, this couldn't be more true. As gravity compresses the gas and dust, the material heats up, creating the intense pressure needed to spark nuclear fusion, the moment a star is born. It's a process that's both elegant and relentless, a testament to the power of this fundamental force. But gravity doesn't work in isolation. While it pulls inward, other forces push back, creating a delicate balance that defines the early stages of star formation. Turbulence within the gas clouds, for instance, can resist gravity's pull, slowing down the collapse. This interplay of forces ensures that stars don't form too quickly or too chaotically, allowing the universe to craft its masterpieces with precision. The role of gravity extends beyond just pulling things together. It also shapes the environment in which stars are born. As dense cores form, they begin to rotate, creating swirling disks of material that will eventually give rise to planets and other celestial bodies. It's a reminder that gravity's influence is far-reaching, shaping not just individual stars but entire solar systems. And yet, gravity is just one piece of the puzzle. While it sets the stage for star formation, other forces like magnetic fields come into play, each adding its own layer of complexity to the process. But that's a story for another blueprint. For now, consider this: every time you look up at the night sky, you're witnessing the handiwork of gravity, the cosmic sculptor that turns the raw elements of the universe into the brilliant stars that light our way. As gravity works its magic, pulling gas and dust into dense cores, another invisible force steps onto the cosmic stage: magnetic fields. These fields are the unsung architects of star formation, weaving intricate patterns into the fabric of stellar nurseries. Think of them as cosmic rivers, gently guiding the flow of material through space. Without magnetic fields, the process of star birth would be far more chaotic, lacking the delicate structure needed to create stable stars. Magnetic fields are born from the movement of charged particles within the gas clouds. As these particles swirl and collide, they generate electric currents, which in turn produce magnetic fields. These fields are incredibly dynamic, stretching and twisting as they interact with the surrounding material. In some ways, they act like invisible hands, shaping the way gas and dust move within a stellar nursery. For instance, they can channel material into long, filamentary structures, creating pathways that lead directly to the heart of a forming star. Recent studies have revealed just how powerful these magnetic fields can be. Astronomers using advanced telescopes have detected fields strong enough to influence the motion of gas over vast distances, even across entire galaxies. This discovery has reshaped our understanding of star formation, highlighting the critical role magnetic fields play in guiding the process. It's like discovering an unseen conductor orchestrating a cosmic symphony, ensuring every note falls into place. One of the most fascinating aspects of magnetic fields is their ability to stabilize collapsing gas clouds. As gravity pulls material inward, magnetic fields create a counterbalance, slowing the collapse and allowing the material to settle into more organized structures. This balance is crucial for the formation of stable stars, preventing the process from becoming too chaotic or too rapid. Without this invisible guidance, stars might form too quickly, burning out before they ever had a chance to shine. But magnetic fields don't just guide the flow of material, they also shape the environment around forming stars. As dense cores rotate, magnetic fields twist and stretch, creating intricate spirals and loops that can later influence the formation of planets. It's a reminder that the birth of a star is rarely a solitary event. Instead, it's part of a larger cosmic dance, with multiple forces working together to create something extraordinary. As magnetic fields continue to shape the journey of star formation, another force is waiting in the wings, ready to add its own layer of complexity. Turbulence, the chaotic yet essential partner in this process, brings a wild unpredictability to the mix. But that's a story for the next blueprint, one that reveals how even chaos can play a vital role in the cosmos. Amid the serene vastness of space, chaos plays a surprisingly vital role. Enter turbulence, the wild, unpredictable force that shapes the cosmic dance of star formation. Imagine a stormy ocean, waves crashing and swirling in every direction. Now, picture that same chaotic energy within a stellar nursery, where gas and dust move in erratic patterns, creating pockets of higher density. This turbulence is the fourth celestial blueprint, a critical ingredient in the recipe for star birth. Turbulence arises from the complex, swirling motions within gas clouds. These chaotic movements cause regions of the cloud to collide and compress, forming dense knots of material. Over time, these knots grow heavier, pulled together by gravity until they reach the tipping point, igniting the spark of a new star. It's a bit like watching cream swirl in a cup of coffee. The random movements create patterns, and within those patterns, something extraordinary can emerge. But turbulence doesn't act alone. It works hand in hand with gravity and magnetic fields, creating a dynamic interplay that defines the star-forming process. While gravity pulls material inward, turbulence pushes it around, ensuring that the collapse isn't too orderly or uniform. This chaotic motion helps distribute energy throughout the cloud, preventing it from collapsing too quickly. Think of it as a cosmic balancing act, gravity providing the pull, turbulence adding the push, and magnetic fields guiding the flow. Together, these forces create the perfect conditions for stars to form. One of the most fascinating aspects of turbulence is its ability to create structure within chaos. Astronomers have observed that turbulent gas clouds often form intricate, filamentary patterns, much like the veins of a leaf or the branches of a tree. These filaments act as highways, channeling material toward the densest regions where stars are born. It's a reminder that even in the midst of disorder, the universe finds a way to organize itself, turning chaos into creation. To understand turbulence better, consider a thunderstorm here on Earth. Within those swirling clouds, pockets of warm air rise, cool air sinks, and wind currents collide, creating a tempest of activity. In a similar way, turbulence in stellar nurseries generates the energy needed to kickstart star formation. Without it, the process would be far more sluggish, and the universe might lack the vibrant tapestry of stars we see today. As turbulence shapes the journey of star formation, it also sets the stage for the next chapter in this cosmic story. Just as turbulent winds can carry heat and energy across vast distances, another force, radiation, plays a crucial role in determining the fate of newborn stars. But that's a story for the next blueprint, where we'll explore how light itself shapes the universe's most luminous creations. As turbulence stirs the cosmic pot, another force steps into the spotlight, one that wields both creation and destruction in equal measure. This is the fifth celestial blueprint, radiation, the double-edged sword of star formation. It's a force of light and energy, capable of igniting the spark of new stars or halting their birth in its tracks. But how does something as intangible as radiation shape the destiny of these cosmic giants? Picture a newborn star, blazing with intensity, its light streaming into the surrounding gas clouds. This radiation doesn't just illuminate the darkness, it interacts with the material around it, heating the gas and dust, and even pushing it away. In some cases, This push can trigger the collapse of nearby clouds, compressing them until they reach the critical density needed to form new stars. It's like a cosmic domino effect, where the energy from one star sets off a chain reaction, birthing others in its wake. But radiation isn't always a catalyst for creation. Sometimes it acts as a barrier. When a massive star emits intense ultraviolet radiation, it can ionize the surrounding gas, stripping electrons from atoms and creating a hot, turbulent environment. This ionized gas resists gravitational collapse, effectively putting a pause on star formation. It's a delicate dance between creation and destruction, where the very force that can bring stars to life can also prevent them from ever forming. Take the Orion Nebula, for example. This iconic star-forming region is a prime illustration of radiation's dual role. Here, massive young stars flood the surrounding clouds with intense radiation, carving out vast cavities in the gas. Within these cavities, new stars are born, their birth triggered by the pressure of the radiation itself. Yet, outside these bubbles, the same radiation creates harsh conditions that stifle star formation. It's a cosmic paradox where light both builds and breaks, all within the same stellar nursery. The balance between radiation pressure and gravitational collapse is a key factor in determining whether a star will form. Radiation pressure can counteract gravity, slowing or even stopping the collapse of a gas cloud. But when the gravitational pull is strong enough, it can override this pressure, allowing the cloud to continue collapsing until a star ignites. This interplay is at the heart of the fifth blueprint, a reminder that star formation is never a straightforward process. It's a tug of war between forces, each vying for dominance in the grand cosmic arena. Radiation's influence extends beyond just the birth of stars. It shapes the environment around them, determining the size, temperature, and even the lifespan of a stellar nursery. Without this force, the universe would lack the diversity of stars we see today, from the smallest red dwarfs to the most massive blue giants. It's a testament to the complexity of the cosmos, where even light itself plays a pivotal role in shaping the universe. As we delve deeper into the mysteries of star formation, another piece of the puzzle awaits. Beyond the forces of gravity, magnetic fields, turbulence, and radiation lies the realm of cosmic chemistry, where the building blocks of stars and planets come together in a symphony of elements. But that's a story for the next blueprint, where we'll explore how the atoms forged in ancient stars give rise to the universe we know today. As we turn our gaze to the sixth celestial blueprint, we find ourselves stepping into the realm of cosmic chemistry, a world where the simplest elements give rise to the most complex creations. Imagine the universe as a master chef, blending ingredients in a cosmic kitchen to craft the stars that light up the night sky. The recipe, a mix of hydrogen and helium, the most abundant elements in the cosmos, combined under extreme conditions that defy imagination. These elements are the building blocks of stars, the raw materials from which the universe shapes its luminous giants. Hydrogen, the lightest and most abundant element, plays the starring role in this cosmic recipe. It's the fuel that powers stars, fusing together under immense pressure and heat to release energy. Helium, its partner in this celestial dance, forms as a byproduct of this fusion, adding another layer to the process. Together, these elements create the foundation upon which stars are built. But how do they come together in the vast emptiness of space? The answer lies in the molecular clouds, the cosmic mixing bowls where star formation begins. Molecular clouds are sprawling regions of gas and dust, rich in hydrogen and helium, that drift through the galaxy. These clouds are more than just passive reservoirs of material. They're dynamic environments where chemistry and physics intertwine. Within their depths, atoms bond to form molecules, creating a chemical tapestry that sets the stage for star formation. Astronomers have discovered that these clouds are not uniform. Instead, they contain pockets of higher density where the conditions are just right for stars to ignite. It's as if the universe has marked certain spots in these clouds with a cosmic X, signaling where the magic will happen. One of the most fascinating aspects of this process is how molecular clouds act as cosmic incubators. As gravity pulls the gas and dust together, the material grows denser and hotter, triggering chemical reactions that pave the way for star birth. These reactions are delicate and precise, requiring just the right balance of temperature and pressure to occur. It's a bit like baking a cake: too much heat and the ingredients burn, too little and they never come together. In the case of stars, the right conditions allow hydrogen atoms to collide and fuse, releasing energy in the form of light and heat. But cosmic chemistry doesn't stop at hydrogen and helium. As stars form, they also create heavier elements like carbon, oxygen, and nitrogen through nuclear fusion. These elements become the building blocks for future generations of stars, as well as planets, moons, and even life itself. It's a reminder that every star is not just a beacon of light, but a factory of creation, enriching the universe with the elements needed for its continued evolution. As we marvel at the chemical processes that shape stars, another factor quietly steps into the spotlight, one that determines whether a star will be born at all. Temperature, the unsung hero of star formation, plays a decisive role in this cosmic drama, but that's a story for the next blueprint, where we'll explore how heat and cold shape the destiny of the universe's most luminous creations. As we peer into the heart of stellar nurseries, one factor quietly dictates the fate of every forming star: temperature. This is the seventh celestial blueprint, a silent force that shapes the delicate balance between creation and collapse. Think of temperature as the cosmic thermostat, regulating the conditions under which stars are born. Too hot, and the gas clouds resist collapse; too cold, and they might never ignite. But when the temperature is just right, it becomes the spark that lights the universe's most brilliant fires. Temperature plays a pivotal role in the earliest stages of star formation. Within the vast clouds of gas and dust, molecules move faster or slower depending on how much heat is present. In colder regions, particles move sluggishly, allowing gravity to pull them together more easily. These frigid pockets are where the seeds of stars first take root, as gravity compresses the material into dense cores. But as these cores grow hotter, something extraordinary happens. The heat generated by this compression can either fuel the birth of a star or halt it entirely, depending on the balance of forces at play. Consider the birth of a massive star, for example. These giants begin their lives in the hottest regions of stellar nurseries, where temperatures can soar to extreme levels. The intense heat creates powerful radiation, which pushes back against the collapsing gas, slowing the process. It's a delicate dance, where the heat of creation must counterbalance the pull of gravity. If the temperature rises too quickly, the gas cloud might dissipate before a star can form. But if the heat is managed just right, it can trigger the ignition of nuclear fusion, the moment a star truly comes to life. On the other hand, smaller stars, like red dwarfs, form in cooler, quieter regions. Here, the lower temperatures allow gravity to work more efficiently, pulling material together without the interference of intense radiation. These stars burn slowly and steadily, a testament to the role temperature plays in determining not just how stars form, but how they evolve over billions of years. It's a reminder that even the smallest variations in heat can lead to vastly different outcomes in the cosmos. The interplay between temperature and other forces like gravity and radiation is what makes star formation such a complex and fascinating process. Gravity pulls material inward, creating heat as the gas compresses. Radiation, in turn, tries to push that heat outward, creating a tug-of-war that defines the early stages of a star's life. Temperature acts as the mediator, ensuring that this balance is maintained long enough for a star to ignite. Yet, temperature doesn't just influence the birth of stars, it shapes their entire life cycle. From the searing heat of their cores to the cooler outer layers, stars are constantly balancing the forces of creation and dissipation. It's a process that underscores the intricate interplay of factors that govern the universe, from the smallest particles to the grandest celestial bodies. As we explore the role of temperature in star formation, another force is waiting in the wings, ready to add its own layer of complexity. Pressure, the invisible hand that shapes the destiny of gas clouds, plays a crucial role in determining whether a star will form or fade away. And that's where our journey takes us next, into the heart of the eighth celestial blueprint. As we delve deeper into the cosmic drama of star formation, another invisible force steps into the spotlight: pressure. This is the eighth celestial blueprint, the cosmic squeeze that shapes the destiny of gas clouds and determines whether a star will emerge from the chaos. Imagine pressure as a cosmic vice, tightening its grip on the swirling clouds of gas and dust. From the outside, external forces compress the material, while from within, the heat generated by collapsing gas creates its own relentless push. Together, these pressures play a crucial role in sculpting the birth of stars. Pressure is the unsung hero of star formation, working silently behind the scenes to balance the forces at play. When a gas cloud begins to collapse under its own gravity, the material at its core grows denser and hotter. This heat creates internal pressure, pushing outward against the gravitational pull. It's a delicate equilibrium, one that must be maintained for a star to form. If the internal pressure becomes too strong, the collapse halts and the cloud dissipates. But if gravity overcomes this pressure, the material continues to compress until nuclear fusion ignites and a star is born. Astrophysicists often describe this process as a cosmic tug-of-war. External pressure, often caused by nearby supernova or the shock waves from other star-forming regions, can compress gas clouds, triggering their collapse. This external squeeze acts like a cosmic hand, nudging the material closer together and setting the stage for gravity to take over. Meanwhile, internal pressure resists this collapse, ensuring that the process doesn't happen too quickly. It's a dance of forces, each playing its part to create the perfect conditions for star birth. To understand this better, think of a balloon. When you squeeze it from the outside, the air inside pushes back with equal force. In a similar way, gas clouds resist external pressure through their internal heat and motion, but unlike a balloon, the stakes are much higher in the cosmos. The balance between these pressures determines whether a cloud will give birth to a star or remain a cold, dark expanse of space. One of the most fascinating aspects of pressure is how it interacts with other forces like gravity and radiation. For example, in regions where massive stars are forming, the intense radiation they emit can create powerful pressure waves that ripple through the surrounding gas. These waves can compress nearby clouds, triggering new rounds of star formation. It's a reminder that the universe is a dynamic, interconnected system, where every force influences the others in profound ways. As we explore the role of pressure in star formation, it's impossible to ignore the subtle yet significant influence of another factor, rotation. Just as pressure shapes the collapse of gas clouds, the spin of these clouds adds another layer of complexity to the process. But that's a story for the next blueprint, where we'll uncover how the universe's rotation guides the birth of stars and the formation of planetary systems. As we continue our journey through the celestial blueprints, we encounter a force that adds a whirlwind of energy to the cosmic dance, rotation. This is the ninth blueprint, the spin of creation that transforms chaotic gas clouds into the elegant disks where stars and planets are born. Imagine a figure skater pulling their arms in, spinning faster and faster. Now, picture that same principle on a cosmic scale, where vast clouds of gas and dust begin to rotate, flattening into disks as they collapse under gravity. These spinning disks are the cradles of future solar systems, where the seeds of stars and planets take root. Rotation begins with a simple concept, angular momentum. Just as a spinning top maintains its motion, gas clouds in space carry this rotational energy, a leftover from the turbulent motions of the universe itself. As gravity pulls these clouds inward, their rotation speeds up, much like the skater spinning faster as they draw their arms closer. This acceleration causes the material to flatten into a disk with the densest region at the center, the birthplace of a new star. The outer edges of these disks, meanwhile, become the raw material for planets, moons, and other celestial bodies. One of the most striking examples of this process can be seen in protostellar disks, the swirling rings of gas and dust observed around young stars. These disks are like cosmic blueprints, revealing the early stages of planetary formation. Astronomers have studied these structures in detail, using advanced telescopes to capture their intricate details. In some cases, they've even spotted gaps within the disks, clear evidence of planets forming, carving out their paths as they orbit their nascent star. It's a breathtaking reminder that the same forces shaping stars also give rise to the worlds that might one day support life. But rotation isn't just about the formation of disks. It also plays a critical role in regulating the birth of stars. As material spirals inward, the angular momentum creates a barrier that slows the collapse, ensuring the process unfolds with precision. Without this spin, gas clouds might collapse too quickly, creating unstable stars or even black holes. Rotation acts as a cosmic brake, allowing the universe to craft its creations with care and balance. The interplay between rotation and gravity is a delicate one. While gravity pulls material toward the center, rotation pushes it outward along the plane of the disk. This balance determines the size and shape of the disk, as well as the eventual distribution of planets within the system. It's a reminder that the birth of a star is never a solitary event. It's part of a larger story, one that includes the formation of entire solar systems. As we marvel at the role of rotation in shaping the cosmos, another force is waiting in the wings, ready to add its own twist to the tale. Feedback mechanisms, the cosmic echoes of star formation, play a crucial role in regulating the process and shaping the universe on a grand scale. But that's a story for the next blueprint, where we'll explore how the birth of one star can influence the destiny of countless others. As the universe crafts its stars, it doesn't do so in silence. Instead, it creates a symphony of feedback mechanisms, cosmic echoes that ripple through space, shaping the birth and death of stars in an endless loop. This is the 10th celestial blueprint, a dynamic interplay of forces that ensures star formation isn't just a one-way process, but a carefully regulated cycle. From the explosive power of supernova to the gentle push of stellar winds, these mechanisms create a delicate balance between creation and destruction, weaving the fabric of the cosmos into an intricate tapestry. Feedback mechanisms begin with the life and death of stars themselves. When a massive star reaches the end of its life, it doesn't fade quietly into the night. Instead, it goes out in a blaze of glory, a supernova. These cataclysmic explosions send shockwaves rippling through nearby gas clouds, compressing the material and triggering the collapse needed to form new stars. It's a cosmic domino effect, where the death of one star gives birth to countless others. The Crab Nebula, for instance, is a stunning example of this process. The remnants of a supernova that lit up the sky nearly 1,000 years ago, it's now a fertile ground for new star formation, its shockwaves still shaping the surrounding clouds. But feedback isn't just about destruction, it's also about influence. Stellar winds, the streams of charged particles flowing from young, massive stars, play a crucial role in regulating star formation. These winds can push gas and dust outward, carving out vast cavities in stellar nurseries. While this might seem counterproductive, it actually helps create the conditions needed for future stars to form. By clearing away excess material, stellar winds allow gravity to focus on denser regions where new stars can ignite. Think of it as a cosmic gardener, pruning the chaos to make space for new growth. One of the most fascinating examples of this process can be found in the Orion Nebula. Here, the intense radiation and stellar winds from massive young stars have sculpted the surrounding gas into intricate shapes, creating a dynamic environment where star formation is both triggered and suppressed. It's a reminder that feedback mechanisms are not just about brute force, they are about balance. Too much feedback and star formation stalls, too little, and the process becomes chaotic. The universe, it seems, has a knack for finding the perfect equilibrium. This delicate balance extends beyond individual star-forming regions. On a larger scale, feedback mechanisms shape the evolution of entire galaxies, determining how quickly stars form and how long they last. They ensure that the cosmos doesn't burn through its fuel too quickly, preserving the conditions needed for stars, planets, and even life to emerge. It's a testament to the interconnectedness of the universe, where every event, no matter how small, has far-reaching consequences. As we explore these feedback mechanisms, it's impossible not to wonder about the forces that lie beyond what we can see. Hidden in the shadows of the cosmos is another mystery, one that shapes the very framework of the universe. Dark matter, the invisible scaffolding that guides the motions of galaxies and the birth of stars, is the next piece of the puzzle, but that's a story for the 11th blueprint, where we'll uncover how the unseen influences the seen in ways we're only beginning to understand. As we peel back the layers of the cosmos, we encounter one of its greatest mysteries, dark matter. This is the 11th celestial blueprint, the invisible force that quietly shapes the universe on a scale we can barely comprehend. Unlike the stars and gas clouds we can see, dark matter doesn't emit light or interact with electromagnetic forces. Yet, its gravitational pull is undeniable, weaving an unseen scaffold that holds galaxies together and guides the birth of stars. Imagine dark matter as the hidden framework of a skyscraper. While we can't see it directly, we know it's there because of the structure it creates. Without it, the universe as we know it would simply fall apart. Dark matter's influence is most evident in the way it shapes galaxies. As stars and gas clouds swirl within a galaxy, they move faster than they should based on the visible matter alone. This discrepancy points to the presence of something unseen, dark matter, whose gravitational pull keeps everything in place. In star-forming regions, this invisible force plays a crucial role in creating the conditions needed for stars to ignite. By pulling gas and dust into dense clumps, dark matter acts like a cosmic sculptor, shaping the raw materials of the universe into the luminous giants we see today. One of the most intriguing aspects of dark matter is how it interacts with the visible universe. While it doesn't collide with ordinary matter, its gravitational influence is profound. Astronomers have observed its effects in the way galaxies cluster together, forming vast cosmic webs that stretch across billions of light years. These webs are like highways, guiding the flow of gas and dust into regions where star formation can thrive. It's a reminder that even the most elusive forces in the universe play a vital role in its evolution. The search for dark matter is one of the most exciting frontiers in modern cosmology. Scientists around the world are working tirelessly to detect this mysterious substance, using everything from underground detectors to powerful particle accelerators. While we haven't yet found direct evidence of dark matter, its presence is inferred from the way it shapes the cosmos. As cosmologist Vera Rubin once said, "We know it's there, but we don't know what it is." This ongoing quest to uncover the nature of dark matter is a testament to humanity's curiosity and determination to understand the universe's deepest secrets. As we contemplate the role of dark matter, another factor quietly steps into the spotlight, one that's just as essential but operates on a completely different scale. Time, the silent architect of the cosmos, plays a pivotal role in shaping the birth and evolution of stars. But that's a story for the next blueprint, where we'll explore how the universe's most elusive dimension influences its most luminous creations. Time, the eternal architect of the cosmos, weaves its influence into every stage of star formation. This is the 12th celestial blueprint, a reminder that the universe operates on a scale far beyond our everyday experience. From the first whispers of a collapsing gas cloud to the fiery ignition of a newborn star, the process unfolds over millions, sometimes billions, of years. It's a timeline so vast that it challenges our understanding, yet it's this very slowness that allows the universe to craft its most spectacular creations with precision. Consider the early moments of star formation, when a dense cloud of gas and dust begins to collapse under its own gravity. This initial stage alone can stretch across hundreds of thousands of years, as the material slowly gathers into a compact core. It's a process that requires patience, both from the universe and from those who study it. Astronomers observing these regions often see them as snapshots frozen in time, each one revealing a different stage of this cosmic journey. For instance, the Orion Nebula offers a glimpse into the early stages, where young stars are still shrouded in the remnants of their birth clouds. Meanwhile, in the Eagle Nebula, towering pillars of gas and dust stand as monuments to the slow, relentless work of gravity over millennia. Time doesn't just shape the birth of stars, it also determines their fate. Take the ignition of nuclear fusion, the moment a star truly comes to life. This critical step depends on the gradual buildup of heat and pressure within the core, a process that can take millions of years. Once ignited, a star's lifespan is dictated by its mass, with smaller stars burning steadily for billions of years and massive stars blazing brightly but briefly before meeting dramatic ends. It's a delicate balance where the passage of time ensures that each star follows its own unique path. The interplay between time and other forces, like gravity and radiation, is equally fascinating. Gravity pulls material inward over eons, while radiation pushes outward, creating a dynamic equilibrium that defines the star-forming process. In regions where massive stars are born, their intense radiation can halt star formation in nearby clouds, delaying the birth of new stars for millions of years. It's a cosmic dance where time acts as both a conductor and a participant, ensuring that every force plays its part in the grand symphony of creation. As we reflect on the role of time in shaping the universe, it's impossible not to marvel at the sheer scale of it all. The birth of a single star is a story written over epochs, a testament to the universe's patience and precision. Yet this story is just one chapter in a much larger narrative, one that spans the entire cosmos. And as we continue our journey through the celestial blueprints, another factor emerges, one that determines not just how stars are born, but what kind of stars they become. Mass, the cosmic sculptor, plays a decisive role in shaping the destiny of stars and the systems they create. But that's a story for the next blueprint, where we'll explore how the weight of a star dictates its life, death, and legacy. As we turn our attention to the 13th celestial blueprint, we encounter one of the most decisive factors in the cosmos: mass, the weight of creation itself. Mass shapes not only the birth of stars, but also their entire life cycle. Imagine a cosmic scale balancing the fate of stellar nurseries. A gas cloud with a little mass might give rise to a modest red dwarf, quietly burning for trillions of years. On the other hand, a massive cloud could ignite a brilliant blue giant, blazing brightly but briefly before its spectacular end. It's a reminder that in the universe, size truly matters, not just in how a star forms, but in how it lives and dies. The role of mass begins with the gas clouds themselves. When a cloud collapses under gravity, the amount of material it contains determines the kind of star that will emerge. Smaller clouds, with less mass, form low-mass stars. These stars, like our Sun, are relatively stable and long-lived, burning their fuel slowly over billions of years. But in the case of massive clouds, the story changes dramatically. The greater the mass, the stronger the gravitational pull, and the hotter and denser the core becomes. This intense environment leads to the birth of massive stars, which burn through their fuel at an astonishing rate, shining with incredible brilliance but living only a fraction of the time. Take, for example, the contrasting lives of a red dwarf and a blue supergiant. Red dwarfs, the smallest and most common stars in the universe, are like the marathon runners of the cosmos. They burn so slowly that some of them will outlive the universe itself. In contrast, blue supergiants are the sprinters, stars like Rigel in the Orion constellation, which burns so fiercely that it exhausts its fuel in just a few million years. The difference lies entirely in their mass, a single variable that dictates their fate from the moment they ignite. But mass doesn't just determine a star's lifespan, it also shapes its evolution. As stars age, they fuse heavier elements in their cores, a process that depends on their initial mass. Small stars, like red dwarfs, never generate enough heat to fuse elements beyond helium. Massive stars, however, forge elements like carbon, oxygen, and even iron in their cores, seeding the universe with the building blocks for planets, life, and future stars. When these giants finally explode as supernova, they scatter these elements across the cosmos, enriching the gas clouds from which new stars will form. It's a cycle of creation and destruction, all driven by the weight of a star's mass. The implications of mass extend far beyond individual stars. On a cosmic scale, the distribution of mass within a galaxy determines how and where stars form. Dense regions, rich in gas and dust, give birth to massive stars that light up their surroundings, while sparser areas produce smaller, dimmer stars. This balance ensures that the universe remains a dynamic and diverse place, filled with stars of every size and brightness. As we marvel at the role of mass in shaping the stars, another factor quietly steps onto the stage, one that influences not just the birth of stars, but their very composition. Metallicity, the measure of elements heavier than hydrogen and helium, plays a crucial role in determining the kind of stars that form and the systems they create. And that's where our journey takes us next, into the realm of the 14th celestial blueprint. As we peel back another layer of the universe's mysteries, we arrive at the 14th celestial blueprint, metallicity, the cosmic seasoning that flavors the birth and evolution of stars. Imagine the universe as a vast kitchen, where hydrogen and helium are the basic ingredients, and heavy elements like carbon, oxygen, and iron are the spices that transform a simple dish into something extraordinary. These elements, forged in the hearts of ancient stars and scattered across the cosmos by supernova, play a crucial role in shaping the stars we see today. But how exactly does this cosmic seasoning influence star formation, and why does it matter? Metallicity refers to the abundance of elements heavier than hydrogen and helium within a gas cloud. In the early universe, when the first stars were born, these clouds were almost purely hydrogen and helium, what astronomers call metal poor. These primordial stars, known as population Roman III stars, were massive and short-lived, burning brightly before exploding and seeding the universe with the first heavy elements. Today, the gas clouds that give rise to stars are richer in these metals, a legacy of those ancient giants. This shift in composition has fundamentally changed the way stars form and evolve. Take, for example, the role of metals in cooling gas clouds. When a cloud collapses under gravity, the heat generated can prevent further collapse unless it's able to radiate away. Metals, with their complex atomic structures, are incredibly efficient at absorbing and releasing this heat, allowing the cloud to cool and condense more easily. This cooling effect is like adding ice to a simmering pot. It lowers the temperature just enough to let gravity work its magic. Without metals, the process of star formation would be far less efficient, and the universe might lack the diversity of stars we see today. But metallicity doesn't just influence how stars form, it also determines what kind of stars they become. In regions with higher metallicity, like the spiral arms of our Milky Way, stars tend to be smaller and more numerous. These stars, like our Sun, are rich in heavy elements, which play a key role in the formation of planets and potentially life. In contrast, low metallicity regions, such as the outskirts of galaxies or the early universe, are more likely to produce massive stars. These giants burn through their fuel quickly, ending their lives in spectacular supernovae that enrich the surrounding gas with even more metals. It's a self-reinforcing cycle, where each generation of stars leaves its mark on the next. Astronomers have observed this interplay in stunning detail, using telescopes to study star-forming regions across the cosmos. In the Large Magellanic Cloud, for instance, a neighboring galaxy with lower metallicity than the Milky Way, massive stars are far more common. This difference in composition has a profound impact on the galaxy's structure and evolution, shaping everything from the brightness of its stars to the distribution of its planets. It's a reminder that the universe is not a static place, it's a dynamic, ever-changing tapestry, woven together by the interplay of forces and elements. As we marvel at the role of metallicity in shaping the cosmos, another factor quietly steps into the spotlight, one that determines not just how stars form, but where. The environment, the cosmic stage on which the drama of star formation unfolds, plays a crucial role in shaping the destiny of gas clouds and the stars they create. And that's where our journey takes us next, into the realm of the 15th celestial blueprint. The environment in which a star is born is like the neighborhood it grows up in, shaping its destiny from the very beginning. This is the 15th celestial blueprint, where we explore how the cosmic surroundings influence the birth of stars. Just as a child's upbringing is shaped by their community, a star's formation is deeply affected by the galaxy it calls home and the specific region within it. Whether it's a bustling spiral galaxy like the Milky Way or a quieter elliptical galaxy, the environment sets the stage for how and where stars come to life. Take spiral galaxies, for example. These vibrant, star-filled structures are some of the most active stellar nurseries in the universe. Their swirling arms are rich with gas and dust, creating the perfect conditions for star formation. Here, the density of material is high, and gravitational interactions between clouds are frequent, triggering the collapse needed to ignite new stars. The Orion Nebula, located in one of the Milky Way's spiral arms, is a prime example of this process in action. Its dynamic environment, filled with young stars and glowing gas, showcases how the right conditions can lead to a burst of stellar activity. On the other hand, elliptical galaxies tell a different story. These older, more settled galaxies are often devoid of the gas and dust needed to form new stars. Instead, they're dominated by aging stars, their golden years marked by a quieter, more stable existence. In these environments, star formation is rare, if it happens at all. The contrast between spiral and elliptical galaxies highlights just how much the cosmic neighborhood can shape the life cycle of stars. But it's not just the type of galaxy that matters. Location within a galaxy plays a crucial role too. In the dense cores of galaxies, where stars and gas are packed tightly together, the intense gravitational forces can trigger rapid star formation. These regions are often home to some of the brightest and most massive stars in the universe. However, the outskirts of galaxies, where material is more spread out, tend to be quieter, with fewer opportunities for stars to form. It's a reminder that even within a single galaxy, the environment can vary dramatically, creating pockets of activity and tranquility. One fascinating example of environmental influence can be seen in dwarf galaxies. These small, often irregular galaxies are like the underdogs of the cosmos, yet they play a vital role in our understanding of star formation. Due to their lower mass and simpler structure, dwarf galaxies can experience bursts of star formation triggered by interactions with larger galaxies or collisions with other dwarf systems. These events stir up the gas and dust, creating the perfect conditions for new stars to ignite. It's a dynamic process, one that shows how even the smallest environments can have a big impact on the universe. As we reflect on the role of environment in shaping the birth of stars, it's impossible not to consider the forces that can disrupt or enhance these conditions. Collisions, for instance, are one of the most dramatic ways that environments can change, setting off chain reactions that reshape entire galaxies. And that's where our journey takes us next, into the realm of cosmic collisions and the extraordinary impact they have on the universe's most luminous creations. In the vast theater of the cosmos, Collisions are the blockbuster events that reshape entire galaxies and ignite the birth of new stars. This is the 16th celestial blueprint, the cosmic crash, a force so powerful it can transform cold, dark gas clouds into blazing stellar nurseries. Imagine two galaxies, each containing billions of stars, hurtling toward each other at unimaginable speeds. When they collide, the result isn't destruction, it's creation. These titanic encounters compress gas clouds, triggering waves of star formation that light up the universe like fireworks in the night sky. One of the most stunning examples of this process can be seen in the Antennae galaxies, a pair of colliding galaxies located about 60 million light-years from Earth. As these two spiral galaxies merge, their gravitational forces pull and twist the gas and dust within them, creating shockwaves that ripple through the material. These shockwaves compress the gas, heating it up and triggering the collapse needed to form new stars. The result is a burst of stellar activity, with thousands of stars igniting in a dazzling display of cosmic fireworks. It's a reminder that even in the chaos of a collision, the universe finds a way to create something beautiful. But galactic collisions aren't the only events that can spark star formation. Even smaller-scale interactions, like the collision of gas clouds within a single galaxy, can have a profound impact. Take, for example, the Orion Molecular Cloud Complex, a star-forming region in our own Milky Way. Here, collisions between smaller gas clouds create pockets of higher density, where gravity can take hold and pull the material together. Over time, these dense regions give birth to new stars, their light illuminating the surrounding gas like lanterns in the dark. It's a process that shows how even the smallest cosmic crashes can have a big impact. The role of collisions in star formation extends beyond just triggering the birth of stars. It also shapes the environment in which they form. In regions where collisions are frequent, like the centers of galaxies or the dense cores of star clusters, the intense gravitational interactions can create a dynamic, ever-changing landscape. Stars are born, live out their lives, and die, all within a relatively short span of cosmic time. This constant cycle of creation and destruction ensures that these regions remain vibrant and active, filled with the light of countless stars. Yet, even as collisions stir up the cosmos, another force is quietly at work, shaping the flow of energy and material in ways we're only beginning to understand. Magnetic reconnection, the process by which magnetic fields break and reform, plays a crucial role in guiding the birth of stars and the evolution of galaxies. And that's where our journey takes us next, into the realm of invisible forces that shape the universe on a scale both vast and intimate. Deep within the swirling chaos of stellar nurseries, another invisible force is at work, one that's as powerful as it is elusive. This is the 17th celestial blueprint, magnetic reconnection, the cosmic spark that ignites the birth of stars. Imagine a tangled web of magnetic fields stretching across vast distances, twisting and snapping like rubber bands under tension. When these fields break and reform, they release bursts of energy so intense they can heat gas clouds, trigger shock waves, and even accelerate particles to nearly the speed of light. It's a process that's as dramatic as it is invisible, shaping the universe in ways we're only beginning to understand. Magnetic reconnection occurs when magnetic field lines, which are normally locked in place, suddenly snap and reconnect in new configurations. This process releases enormous amounts of energy, much like a coiled spring suddenly releasing its tension. In the context of star formation, this energy can heat the surrounding gas, creating the conditions needed for gravity to pull material together and ignite new stars. Think of it as a cosmic spark plug, firing up the engine of creation in the heart of a stellar nursery. One of the most fascinating aspects of magnetic reconnection is its ability to influence entire star-forming regions. Astrophysicists have observed this phenomenon in regions like the Orion Nebula, where magnetic fields play a crucial role in shaping the flow of gas and dust. When these fields reconnect, they can create shock waves that ripple through the cloud, compressing material and triggering the collapse needed to form stars. It's a delicate balance, where the invisible forces of magnetism and gravity work together to craft the universe's most luminous creations. But magnetic reconnection isn't just about star birth. It also plays a role in the life and death of stars. In the outer layers of stars, magnetic fields can twist and snap, releasing bursts of energy that power solar flares and coronal mass ejections. These events, while dramatic, are also part of the natural cycle of stellar evolution, shaping the environment around stars and influencing the formation of planets. It's a reminder that the universe is a dynamic, interconnected system, where even the smallest forces can have far-reaching consequences. Recent studies have shed new light on the importance of magnetic reconnection, with astrophysicists using advanced simulations and telescopes to observe this process in action. These observations have revealed just how powerful this phenomenon can be, with energy releases equivalent to millions of atomic bombs. It's a testament to the complexity of the cosmos, where even the most subtle forces can shape the birth and evolution of stars. As we marvel at the role of magnetic reconnection in shaping the universe, another force is waiting in the wings, ready to add its own layer of mystery. Cosmic rays, the high-energy particles that streak through space, play a crucial role in shaping the environment of star-forming regions, and that's where our journey takes us next, into the realm of particles that travel at nearly the speed of light, influencing the birth of stars in ways we're only beginning to uncover. Cosmic rays, the invisible messengers of the universe, streak through space at nearly the speed of light, carrying with them the energy to influence the birth of stars. This is the 18th celestial blueprint, where we uncover how these high-energy particles shape the delicate dance of star formation. Unlike the steady glow of starlight or the gentle tug of gravity, cosmic rays are the wild cards of the cosmos, tiny yet powerful. They leave their mark on the gas clouds that give rise to new stars. But how exactly do these particles, born from the most violent events in the universe, impact the quiet process of star birth? Cosmic rays are essentially high-energy protons and atomic nuclei, accelerated to incredible speeds by supernova, black holes, and other extreme cosmic phenomena. When these particles collide with the gas and dust in a stellar nursery, they ionize the material, stripping electrons from atoms and creating charged particles. This ionization process has a profound effect on the behavior of gas clouds. It increases the cloud's ability to conduct electricity, which in turn strengthens magnetic fields. These fields, as we've seen in earlier blueprints, play a crucial role in guiding the flow of material and regulating the collapse of gas into stars. One striking example of this influence can be found in the Taurus molecular cloud, a star-forming region located just over 400 light-years from Earth. Here, astronomers have observed that cosmic rays help maintain the ionization levels needed for magnetic fields to remain active. These fields, in turn, stabilize the cloud, preventing it from collapsing too quickly and ensuring that stars form at a steady, controlled pace. It's a delicate balance, where the energy of cosmic rays acts as a subtle but essential ingredient in the recipe for star formation. But cosmic rays don't work alone. They interact with other forces, like radiation, to shape the environment of stellar nurseries. In regions where massive stars are forming, their intense radiation can suppress the effects of cosmic rays, creating a dynamic interplay between these two forces. This balance determines how quickly gas clouds collapse and how efficiently stars are born. It's a cosmic tug-of-war where the outcome depends on the relative strength of these competing influences. The role of cosmic rays in star formation isn't just about their immediate impact on gas clouds, it's also about their long-term influence on the evolution of galaxies. By ionizing gas and strengthening magnetic fields, cosmic rays help regulate the rate at which stars form, ensuring that galaxies don't burn through their fuel too quickly. This process is essential for maintaining the diversity and stability of the universe, allowing stars, planets, and even life to emerge over billions of years. As we explore the influence of cosmic rays, another force quietly steps onto the cosmic stage, one that channels the energy of star formation into powerful, focused streams. Protostellar jets, the fiery outflows from young stars, are the next piece of the puzzle. These jets, driven by the intense magnetic fields and rotation of newborn stars, carve out pathways in the surrounding gas, shaping the environment in which future stars will form. And that's where our journey takes us next, into the realm of these spectacular cosmic fountains. In the heart of stellar nurseries, where gas and dust swirl in the dance of creation, another breathtaking phenomenon emerges: protostellar jets. These are the 19th celestial blueprint, the cosmic outflows that carve their way through the chaos of star-forming regions. Picture a newborn star, still wrapped in its cocoon of gas, as it begins to unleash narrow, high-speed streams of material into space. These jets, stretching light years across, are not just byproducts of star formation, they are powerful sculptors, shaping the environment around them and influencing the birth of future stars. Protostellar jets are born from the intense magnetic fields and rapid rotation of young stars. As material spirals inward, drawn by gravity toward the forming star, some of it is funneled along magnetic field lines and ejected outward at incredible speeds. These jets can reach velocities of hundreds of kilometers per second, blasting through the surrounding gas and dust like cosmic blowtorches. In the process, they carve out cavities and channels, clearing paths that allow radiation to escape and preventing the star from being smothered by its own birth cloud. It's a delicate balancing act, one that ensures the young star can continue to grow and shine. One of the most striking examples of this process can be seen in the Herbig-Haro objects, glowing patches of gas illuminated by the collision of protostellar jets with surrounding material. These objects, named after astronomers George Herbig and Guillermo Haro, are like cosmic signposts, marking the presence of young stars and their powerful outflows. In the Orion Nebula, for instance, Herbig-Haro objects dot the landscape, their bright, wispy shapes revealing the dynamic interplay between jets and gas. It's a vivid reminder that star formation is not a quiet, isolated event. It's a vibrant, interconnected process where the actions of one star can ripple through an entire region. The influence of protostellar jets extends far beyond their immediate surroundings. By clearing away excess material, they help regulate the rate at which stars form, ensuring that gas clouds don't collapse too quickly or chaotically. They also play a role in redistributing energy and momentum throughout the stellar nursery, creating the conditions needed for future generations of stars to ignite. In a sense, these jets are cosmic gardeners, tending to the gas clouds and shaping the environment in which new stars will grow. But the story of protostellar jets is just one chapter in the larger tale of star formation. As these jets carve their paths through the cosmos, they leave behind another critical structure, one that plays a central role in the birth of stars and planets. Accretion disks, the swirling rings of gas and dust that surround young stars, are the next piece of the puzzle. These disks, rich with material and potential, are the cosmic cradles where planets take their first steps toward existence. And that's where our journey takes us next, into the heart of these spinning reservoirs of creation. Surrounding young stars like dazzling halos, accretion disks are the 20th celestial blueprint, the cosmic whirlpools that fuel the growth of these newborn giants. Picture a swirling storm of gas and dust, spinning rapidly around a central point, funneling material inward to feed the growing star. These disks, often stretching billions of kilometers across, are more than just leftovers from the star's birth. They're the lifeblood of its early existence, the reservoirs of energy that sustain its growth and shape its future. Without these spinning structures, stars would struggle to gather the mass and momentum needed to ignite and shine. Accretion disks form as material from the surrounding gas cloud spirals inward, drawn by the star's gravity. But instead of falling straight into the star, this material begins to orbit, creating a flat, rotating disk. Think of it like water circling a drain, except here, the drain is a star, and the swirling water is a chaotic mix of gas, dust, and magnetic fields. Over time, friction and magnetic forces within the disk cause the material to lose energy, slowly spiraling closer to the star until it's absorbed, fueling the star's growth and brightness. Astronomers have observed these disks in stunning detail, using telescopes like the Atacama Large Millimeter Array ALMA to capture their intricate structure. These observations reveal that accretion disks are far from uniform. Instead, they're dynamic, ever-changing environments, with pockets of higher density and regions where material clumps together, forming the seeds of future planets. In fact, these disks are the birthplace of solar systems, the cosmic cradles where planets, moons, and asteroids first take shape. It's a reminder that the birth of a star is rarely a solitary event. It's the beginning of an entire system's story. One of the most fascinating aspects of accretion disks is their ability to regulate the growth of young stars. As material flows inward, it releases energy in the form of heat and light, creating a feedback loop that can slow or speed up the star's growth. In some cases, this process can even trigger powerful outbursts, as the star suddenly absorbs a large amount of material, flaring brightly in a phenomenon known as a FU Orionis event. These outbursts are like cosmic growth spurts, reminding us that even stars have moments of dramatic change. Yet, accretion disks are not just passive feeders, they are active participants in the star-forming process. Their rotation and magnetic fields can channel material into jets, like the ones we explored earlier, creating the spectacular outflows that shape the surrounding gas clouds. This interplay between the disk and the star highlights the complexity of star formation, where every force and structure plays a role in crafting the universe's most luminous creations. As we marvel at the role of accretion disks, another force is waiting to take center stage, one that stems from the most massive stars in the universe. The feedback from these giants, through their intense radiation and stellar winds, can reshape entire star-forming regions, influencing the birth and evolution of countless stars. And that's where our journey takes us next, into the realm of stellar feedback and its profound impact on the cosmos. Massive stars are the titans of the cosmos, blazing with such intensity that they don't just light up the night, they shape the very fabric of the universe. This is the 21st Celestial Blueprint, where we explore how these stellar giants act as cosmic regulators, influencing the birth and death of stars through their powerful feedback. Imagine a massive star as a sculptor, wielding tools of radiation, stellar winds, and explosive supernova to carve out the future of its surroundings. These stars don't just exist in isolation, they leave a lasting legacy, their energy and material rippling through the cosmos, shaping the destiny of entire star-forming regions. At the heart of this feedback process is radiation. Massive stars emit intense ultraviolet light, so powerful that it can ionize the gas around them, stripping electrons from atoms and heating the surrounding material. This radiation creates vast bubbles of ionized gas, known as H-II regions, which glow brightly and push against the colder, denser gas clouds nearby. In the Orion Nebula, for instance, the massive stars of the trapezium cluster have carved out a cavity in the surrounding gas, their radiation triggering new waves of star formation along the edges of this bubble. It's a cosmic domino effect, where the light from one star sparks the birth of countless others, but radiation isn't the only tool in a massive star's arsenal. Stellar winds, the powerful streams of charged particles flowing from these giants, also play a crucial role. These winds can reach speeds of thousands of kilometers per second, sweeping through the surrounding gas and dust, compressing it, and triggering the collapse needed to form new stars. In some cases, these winds are so intense that they can blow away entire gas clouds, halting star formation entirely. It's a delicate balance. Massive stars can both create and destroy, their influence shaping the fate of stellar nurseries in profound ways. Perhaps the most dramatic form of feedback comes from supernova, the explosive deaths of massive stars. When a star reaches the end of its life, it doesn't fade quietly. It goes out with a bang, releasing an unimaginable amount of energy in a matter of seconds. These explosions send shockwaves rippling through the surrounding gas, compressing it and triggering new waves of star formation. The Crab Nebula, the remnant of a supernova observed nearly 1,000 years ago, is a stunning example of this process. Its shockwaves continue to shape the surrounding gas, creating the conditions needed for new stars to ignite. It's a reminder that even in death, massive stars give life to the cosmos. The feedback from massive stars is not just about creation, it's also about regulation. By heating, compressing, and dispersing gas, these stars ensure that star formation doesn't happen too quickly or too chaotically. They create a dynamic, ever-changing environment where the birth of one star influences the fate of countless others. This balance between creation and destruction is at the heart of the cosmic dance, a testament to the interconnectedness of the universe. As we marvel at the role of massive stars as cosmic regulators, another intriguing factor steps into the spotlight, one that adds a layer of complexity to the star-forming process. Binary systems, where two stars orbit each other, play a crucial role in shaping the birth and evolution of stars. These systems, with their unique dynamics and interactions, offer a fascinating glimpse into the universe's intricate web of creation. And that's where our journey takes us next, into the realm of stellar partnerships and their profound influence on the cosmos. In the vast expanse of the cosmos, stars rarely dance alone. Enter the 22nd Celestial Blueprint, binary systems, the cosmic duos that add a fascinating layer of complexity to the story of star formation. Picture two stars locked in an eternal gravitational embrace, orbiting each other in a delicate balance of attraction and motion. These systems, where two stars share a common center of gravity, are more than just celestial curiosities. They're dynamic partnerships that shape the birth, evolution, and even the death of stars in ways that solitary stars never experience. Binary systems form much like single stars from the collapse of a gas cloud, but instead of a single dense core, the cloud fragments into two, creating a pair of stellar siblings. These stars can be close enough to share material or distant enough to barely influence one another. In some cases, they're born together from the same cloud, while in others, they're brought together later by gravitational interactions. The result is a system where the stars' fates are intertwined, their evolution shaped by their mutual influence. One of the most striking examples of this dynamic can be found in Sirius, the brightest star in our night sky. Sirius is actually a binary system, consisting of a bright main sequence star and a faint white dwarf companion. These two stars orbit each other every 50 years, their gravitational dance a testament to the enduring bond between stellar partners. This system shows how binary stars can evolve together, with one star transitioning into a white dwarf while the other continues to shine brightly. But binary systems aren't just about companionship, they're also about interaction. In close binaries, the stars can exchange material, with one star pulling gas from its companion in a process known as mass transfer. This can lead to dramatic changes in both stars, altering their size, temperature, and even their ultimate fate. For example, if one star in a binary system becomes a red giant, it can transfer material to its companion, potentially triggering a supernova or creating exotic objects like neutron stars or black holes. It's a cosmic collaboration that reshapes the stars and the systems they inhabit. The influence of binary systems extends beyond just the stars themselves. Their gravitational interactions can also shape the surrounding environment, triggering waves of star formation or even disrupting the orbits of nearby planets. In star-forming regions like the Orion Nebula, binary systems are common, their presence adding another layer of complexity to the already intricate process of stellar birth. These systems remind us that the universe is a place of connection and interaction, where even the stars are rarely alone. As we marvel at the intricate dynamics of binary systems, it's impossible not to wonder how these stellar partnerships fit into the larger picture. In the bustling neighborhoods of star clusters, where hundreds or even thousands of stars are born together, binary systems are just one piece of a much larger puzzle. These clusters, with their dense concentrations of stars and gas, are the next chapter in our exploration of the celestial blueprints, a story of collective creation and cosmic community. In the vast tapestry of the cosmos, stars often come together in dazzling gatherings, stellar communities that shine brighter than the sum of their parts. This is the 23rd celestial blueprint, star clusters, the cosmic neighborhoods where stars are born, live, and evolve side by side. Picture a bustling city where every light is a star and every street is a pathway of gravitational connection. These clusters, ranging from a few dozen stars to hundreds of thousands, are more than just beautiful arrangements, they're dynamic environments where the birth of one star influences the lives of countless others. But how do these cosmic communities form, and what makes them such essential players in the story of star formation? Star clusters begin their lives in the densest regions of molecular clouds, where vast amounts of gas and dust collapse under gravity. Unlike solitary stars, which form in isolation, clusters emerge from the fragmentation of these massive clouds, giving rise to dozens or even hundreds of stars at once. It's a cosmic explosion of creation, where the energy of one collapsing cloud ignites a cascade of stellar births. These newborn stars remain bound together by gravity, forming a tight-knit community that evolves as a single entity. One of the most famous examples of this process is the Pleiades, a young open cluster visible to the naked eye. Located about 440 light-years from Earth, the Pleiades is home to hundreds of stars, all born from the same gas cloud roughly 100 million years ago. These stars, still glowing with the brightness of youth, share a common origin and a gravitational bond that keeps them close. Yet over time, this bond will weaken, and the cluster will gradually disperse, its stars drifting apart to join the broader galaxy. It's a reminder that even the tightest cosmic communities are not forever. They're fleeting moments in the grand timeline of the universe. But star clusters aren't just about the stars they contain. They're also about the interactions between them. In these dense environments, stars are constantly influencing one another, their gravitational pull shaping the dynamics of the cluster. Close encounters can alter a star's trajectory, while the collective gravity of the cluster can trap interstellar gas, creating the conditions for new stars to form. It's a delicate balance where the actions of one star ripple through the entire community, shaping its evolution in profound ways. Globular clusters, on the other hand, tell a different story. These ancient communities, often containing hundreds of thousands of stars, are some of the oldest structures in the universe. Unlike open clusters, which are relatively young and loosely bound, globular clusters are tightly packed, their stars orbiting a common center like bees in a hive. The Omega Centauri cluster, for instance, is a stunning example of this longevity. With millions of stars densely packed into a region just 150 light-years across, it's a testament to the enduring power of gravitational bonds. These clusters offer a glimpse into the early universe, their ancient stars holding clues to the processes that shaped the cosmos billions of years ago. The interplay between individual stars and the cluster as a whole is what makes these communities so fascinating. Each star, while part of a larger system, follows its own unique path, shaped by the gravitational forces at play. Yet, the cluster itself acts as a single entity, its collective behavior influencing the evolution of its members. It's a cosmic dance of connection and individuality, where the whole is greater than the sum of its parts. As we marvel at the complexity and beauty of star clusters, another cosmic stage comes into view, one that shapes not just individual stars or clusters, but the destiny of entire galaxies. Galactic centers, the bustling hubs of star formation, are the next chapter in our exploration of the celestial blueprints. These regions, teeming with activity and energy, are where the universe's most dramatic events unfold, shaping the birth and evolution of stars on a grand scale. And that's where our journey takes us next, into the heart of the galaxy itself. At the heart of every galaxy lies a cosmic powerhouse, a region of unimaginable energy and activity that shapes the destiny of countless stars. This is the 24th celestial blueprint, galactic centers, the bustling hubs where star formation reaches its most dramatic and intense levels. Picture the core of a galaxy as a colossal engine, driven by the immense gravity of a supermassive black hole and surrounded by swirling clouds of gas and dust. Here, in this chaotic and energetic environment, stars are born under conditions unlike anywhere else in the universe. But what makes these galactic centers so unique, and how do they influence the birth of stars in ways that challenge our understanding of the cosmos? The key to understanding galactic centers lies in their extreme environments. At the core of most galaxies, including our own Milky Way, sits a supermassive black hole, a gravitational behemoth millions or even billions of times more massive than our Sun. These black holes are not just passive observers, they are active participants in the cosmic dance, their immense gravity shaping the flow of gas and dust around them. As material spirals inward, it forms an accretion disk, a swirling ring of superheated gas that glows brightly with the energy of creation. This disk, in turn, can trigger intense bursts of star formation, as the gravitational forces compress nearby gas clouds and ignite new stars. One of the most striking examples of this process can be seen in the galaxy NGC 1068, located about 47 million light-years from Earth. Here, astronomers have observed a supermassive black hole surrounded by a dense, rotating disk of gas. The intense radiation and gravitational forces from the black hole have created a turbulent environment where gas clouds are compressed and heated, leading to the birth of new stars. This galaxy is a vivid illustration of how the most extreme environments in the universe can also be the most fertile grounds for stellar creation. But the influence of galactic centers isn't just about the black holes themselves. The surrounding regions are often filled with dense molecular clouds, where the sheer volume of material creates ideal conditions for star formation. In the Milky Way's galactic center, for instance, the central molecular zone is a region packed with gas and dust, where stars are born at a rate far higher than in the outer regions of the galaxy. These stars, however, face unique challenges, from the intense radiation of nearby supermassive black holes to the powerful gravitational forces that can tear apart gas clouds before they fully collapse. Despite these challenges, galactic centers are also places of incredible opportunity. The same forces that make these regions hostile can also drive the creation of massive stars and star clusters, some of the most luminous and dynamic objects in the universe. In the galaxy M82, for example, the intense star formation near the galactic center has created a starburst region, where stars are born at a rate hundreds of times faster than in our own galaxy. This frenzy of creation is a testament to the power of galactic centers, where the universe's most extreme conditions give rise to its most spectacular phenomena. As we explore the role of galactic centers in star formation, it's impossible not to wonder what the future holds for our understanding of these cosmic powerhouses. With new telescopes and advanced technologies on the horizon, astronomers are poised to uncover even more about the intricate processes that shape the birth of stars in these dynamic environments. And as we continue to unravel these mysteries, we gain not just a deeper understanding of the universe, but also a greater appreciation for the beauty and complexity of the cosmic dance. The story of star formation is far from over. It's a journey that continues to unfold, revealing new wonders with every discovery. As we stand on the precipice of a new era in astronomy, the study of star formation is entering a golden age of discovery. Over the past few decades, we've uncovered incredible insights into how stars are born, from the delicate collapse of gas clouds to the explosive feedback of massive stars. Yet for every mystery solved, a dozen new questions arise, each one beckoning us to look deeper into the cosmos. The 25th celestial blueprint isn't just about what we know, it's about the tools and technologies that will help us uncover what we don't. And at the forefront of this revolution is the James Webb Space Telescope, a marvel of engineering poised to transform our understanding of the universe. Launched in late 2021, the James Webb Space Telescope, or JWST, represents a quantum leap in our ability to observe the cosmos. With its massive gold-coated mirror and cutting-edge infrared sensors, JWST can peer through the dust and gas of stellar nurseries, revealing the earliest stages of star formation in unprecedented detail. Already, it has delivered breathtaking images of star-forming regions like the Orion Nebula, capturing the intricate dance of gas, dust, and newborn stars in ways we've never seen before. But its impact goes far beyond stunning visuals. JWST is helping astronomers study the chemical composition of these regions, uncovering the building blocks of stars and planets in ways that were once impossible. Yet, JWST is just the beginning. New ground-based observatories, like the extremely large telescope currently under construction in Chile, will complement its efforts, offering even sharper views of the universe. These telescopes, equipped with adaptive optics to correct for Earth's atmospheric distortions, will allow us to study star formation in galaxies billions of light-years away. By combining data from space and ground-based instruments, astronomers hope to piece together a more complete picture of how stars form across different environments, from the quiet outskirts of galaxies to the chaotic cores of galactic centers. But technology alone isn't enough to unravel the mysteries of star formation. It's the people behind the instruments, the astronomers, astrophysicists, and researchers who drive this field forward. Dr. Jane Rigby, an astrophysicist working with JWST, describes this moment as a renaissance in astronomy, where every observation brings us closer to understanding the universe's most fundamental processes. Her excitement is shared by many in the field, who see the next decade as a time of unparalleled opportunity. From studying the role of magnetic fields in star formation to exploring the impact of dark matter, the questions being asked today are as bold as they are profound. What makes this era particularly exciting is the collaborative nature of modern astronomy. No longer confined to isolated observatories, researchers now share data across the globe, pooling their expertise to tackle the universe's biggest questions. Projects like the Sloan Digital Sky Survey and the upcoming Vera-C Rubin Observatory are creating vast archives of astronomical data, enabling researchers to analyze star-forming regions on an unprecedented scale. This collaborative spirit, combined with cutting-edge technology, is opening doors to discoveries that were once unimaginable. As we look to the future, it's clear that the study of star formation is far from complete. Each new discovery raises new questions. Each new tool offers new possibilities. What drives the formation of the first stars in the early universe? How do binary systems and star clusters influence the evolution of galaxies? And what role do cosmic rays and magnetic fields play in shaping the birth of stars? These are just a few of the mysteries waiting to be unraveled, and the answers promise to reshape our understanding of the cosmos. In the final chapter of this journey, we'll bring together everything we've learned, weaving the 25 celestial blueprints into a cohesive story of creation, evolution, and discovery. From the humble beginnings of a collapsing gas cloud to the dazzling complexity of galactic centers, the universe's story is one of endless wonder. And as we continue to explore, we're reminded that every star we see is not just a point of light. It's a testament to the universe's boundless creativity and the human spirit's unyielding curiosity. The future of star formation research is bright, and the discoveries ahead will undoubtedly inspire generations to come. As we bring our journey through the 24 celestial blueprints for star formation to a close, it's impossible not to marvel at the intricate web of forces and processes that shape the universe. From the delicate collapse of gas clouds to the explosive feedback of massive stars, each blueprint reveals a piece of the cosmic puzzle, showing us how the universe transforms chaos into creation. These blueprints aren't isolated steps, they're interconnected threads in a grand tapestry, each one influencing and being influenced by the others. Together, they form a symphony of forces, a harmony of gravity, radiation, magnetism, and time that guides the birth of stars and the evolution of galaxies. At the heart of this story is balance. Gravity pulls, radiation pushes, magnetic fields guide, and turbulence stirs, creating a dynamic equilibrium that allows stars to form and thrive. Feedback mechanisms, from the gentle winds of young stars to the cataclysmic explosions of supernova, regulate this process, ensuring that star formation doesn't happen too quickly or too chaotically. Even the environment, whether it's the bustling core of a galaxy or the quiet outskirts of a molecular cloud, plays a crucial role, shaping the conditions under which stars are born. It's a reminder that the universe is not a static place, but a living, breathing system, constantly evolving and adapting. What makes these blueprints so extraordinary is their universality. Whether we're looking at the birth of a single star in our own galaxy or the formation of entire star clusters in distant galaxies, the same principles apply. The forces that shaped the first stars billions of years ago are the same ones at work today, crafting the luminous giants we see in the night sky. This continuity is a testament to the elegance and consistency of the cosmos, a reminder that the universe operates by rules we can uncover and understand. Yet, for all we've learned, the universe remains full of mysteries. Every discovery raises new questions, every observation opens new doors. The James Webb Space Telescope and other cutting-edge instruments are giving us glimpses of star formation in unprecedented detail, but there's still so much we don't know. How do the first stars form in the early universe? What role do dark matter and cosmic rays play in shaping stellar nurseries? And how do the tiniest fluctuations in temperature and density lead to the birth of stars and planets? These are the questions that drive astronomers and astrophysicists, fueling a quest for knowledge that spans generations. As we reflect on the awe-inspiring complexity of the universe, let's remember the words of Carl Sagan: "Somewhere, something incredible is waiting to be known." This sentiment captures the essence of our journey, a journey not just of discovery, but of wonder. The stars above are more than just points of light. They're windows into the past, present, and future of the cosmos. They remind us of our place in the universe, not as passive observers, but as active participants in the quest to understand it. So, as we conclude this exploration, I invite you to look up at the night sky with a renewed sense of curiosity. What mysteries will we uncover next? What stories do the stars still have to tell? Share your thoughts in the comments below. I'd love to hear what inspires you about the cosmos. And if you've enjoyed this journey through the celestial blueprints, don't forget to subscribe and join us as we continue to unravel the mysteries of the universe. The cosmos is vast, and the adventure is just beginning. Thank you for watching, and may your curiosity always burn as brightly as the stars.